Now, before I look at a proof of de Moivre's theorem for rational numbers, I want to look at a proof of it for n equals minus 1. So we have cos theta plus I sine theta to the power of minus 1, and we want to prove that this is equal to cos of minus 1 times theta, or minus theta, plus I sine minus theta. What we do is use the result of a previous video. Cos theta plus I sine theta to the power of minus 1 is just 1 divided by cos theta plus I sine theta to the power of 1. Of course, we don't have to write in that. And in the division video, which is a few videos back, video on the division of complex numbers that are in polar form, we saw that this here is cos of minus theta plus I sine of minus theta. But you see that this thing here is just got by multiplying minus 1 by theta. Minus 1 times theta is minus theta. So now you see that de Moivre's theorem is true for n equals minus 1. What about de Moivre's theorem for n equals minus 2? Well, we can write this thing here as cos theta plus I sine theta to the power of minus 1, and put all of this here to the power of 2. Because to get rid of these outer brackets, we just multiply the powers. We just multiply 2 by minus 1 to get minus 2. But we already know what this thing here is. We know that it's cos minus theta plus I sine minus theta. And it's all raised to the power of 2. Now in the last video, we proved de Moivre's theorem for the case where the power is a positive integer or a natural number. So we know what to do with this. We know that we can multiply this power by the argument, because it's an element of the natural numbers. We proved that situation in the previous video. So multiplying by 2, we get cos minus 2 theta plus I sine of minus 2 theta. So that proves de Moivre's theorem for n equals minus 2. We can multiply minus 2 by the angle. We can now easily generalize that result to the case where n is any negative integer. So let n equal minus k, where k is a natural number. So for example, k could be 3. So in that case, n would equal minus 3. Or k could be 10. K has to be a natural number, a positive integer. Then n would be minus 10. And so on. So I've just replaced the number 2 with k. So we can write this thing here like this, because if we multiply k by minus 1, we get back minus k. We apply de Moivre's theorem for the case when n is minus 1, which we proved previously. Just multiply minus 1 by the angle. And you can then see that we have a complex number in polar form raised to the power of a positive integer or a natural number. K is an element of n. So we can use the result of the previous video, which states that de Moivre's theorem is true when the power is a natural number. So we just multiply the power by the argument. So now we've proven de Moivre's theorem for all integers, not just positive integers, but negative integers as well. And we proved it for n equals 0 also in the previous video. So the letter Z denotes the set of all integers, that is positive and negative whole numbers, including 0. Now let's look at de Moivre's theorem for n an element of Q. Q stands for the set of rational numbers, that is ratios of whole numbers or fractions. So a rational number has the form a over b, where a and b are integers. B cannot be 0, because we can't divide by 0. So rational numbers include all the integers. For example, an integer like minus 7 can be written as a rational number. It can be written as minus 7 over plus 1. Minus 7 and plus 1 are both integers. So this is a larger set. It includes all the integers, and all the integers include all the natural numbers. So the set of natural numbers is a subset of the set of integers z, which in turn is a subset of all the rational numbers q. To illustrate what I'm going to do, I'm going to start off with this example. I'm going to start off of the example where n is equal to a half. 1/2 is a rational number. It's not an integer. So here is the Moivre's theorem for n equals a half. So what I want to do is prove that this thing here is cos of a half theta plus I sine of a half theta. We should just have to multiply the power by the argument. Let's see if this is true. What we note is that if we take cos theta plus I sine theta to the power of a half and multiply it by itself, well, we just add the powers. A half plus a half gives us 1. We get cos theta plus I sine theta to the power of 1. You could also think of this as the square root of cos theta plus I sine theta. The square root of a number times itself gives that number. Now let's look at the complex number cos theta plus I sine theta to the power of a half. It's going to be a complex number because the set of complex numbers is the largest set we've spoken about. Any complex number raised to a power, whether that power is real or complex or whatever, will give us a complex number. And we know that complex numbers can be written in polar form. That means that the complex number has some argument a. Now how a is related to theta we're going to find out. What about the modulus of this complex number? Well, if we look at the modulus of cos theta plus I sine theta, we see that it's 1. So you could have a 1 to the power of a half here. The modulus of cos theta plus I sine theta is cos squared theta plus sine squared theta, or the square root of cos squared theta plus sine squared theta, which is the square root of 1, which is 1, because cos squared theta plus sine squared theta is equal to 1, no matter what theta is. So we just square the real part, square the imaginary part, sum them, and get the square root. That's how we find the modulus. So the modulus of what's in here is 1, and when we put 1 to the power of a half, well, 1 to the power of anything is just 1. So the modulus of our result is also 1. So the modulus of this number is 1, or cos squared a plus sine squared a, which is 1, of course. So we don't have to worry about the modulus in this case. So we're dealing with complex numbers of unit length, if you like. So now we know that we can write these two complex numbers as cos a plus sine a, I sine a, and if we multiply them together, what do we get? Well, by a previous video on the multiplication of complex numbers that are in polar form, you saw that we just add the arguments. So we add a onto a to get 2a. We don't have to worry about the moduli. The modulus of this is 1, the modulus of this is 1. We'd normally multiply the two moduli together, but 1 times 1 will just give us 1. Okay, so we just add the arguments to get this single complex number, and it must equal the right hand side, which is cos theta plus I sine theta. So the only way that two complex numbers can equal each other is if the real parts are equal and if the imaginary parts are equal. So you can see straight away that if the real parts are equal, if cos 2a equals cos 2 theta, then 2a must equal theta, which means that a equals a half theta. Actually, there is more than one value of a. We're dealing with a multi-valued function here. Cos theta plus I sine theta to the power of a half has multiple values. It actually has at most 2 values. I'll talk about that in the next video. But for now I just want to show you one of those values. And so this is it here. A is a half theta. So we can multiply a half by this angle. So this is one of the values. So de Moivre's theorem is true for n equals a half. Now let's look at a more general situation. Let's consider the case where n is equal to 1 over b, where b is a natural number. So for example, n could equal 1/3. It could equal, say, 1 over 100. Okay, so we're going to deal with the case where n is positive, because b is obviously a positive integer. So we're interested in looking at this, and we want to see if this is equal to cos of 1 over b times theta plus I sine of 1 over b times theta. Now if we take cos of theta plus I sine of theta to the power of 1 over b and multiply it out b times. So what we have here are b terms, where a term is cos theta plus I sine theta. So in the previous example we had that b was 2. We had cos theta plus I sine theta to the power of a half. So we just had two terms. Cos theta plus I sine theta to the power of a half times cos theta plus I sine theta to the power of a half gave us cos theta plus I sine theta to the power of 1. If we have b terms here, we just add up all the powers. So we have 1 over b plus 1 over b plus dot dot dot. We have b 1 over b's. b times 1 over b is just 1. So we get cos theta plus I sine theta to the power of 1. And like before, this here is a complex number whose argument is a, which we're going to find out, and whose modulus is 1, because the modulus of cos theta plus I sine theta is 1. And if we raise 1 to the power of 1 over b, we could write this out more fully as we take the modulus out, which is 1. So we'd have 1 to the power of 1 over b, but 1 to the power of anything is 1. So the modulus of this number is 1. Because cos squared a plus sine squared a is 1. Anyway, so we have this thing multiplied out b times. And we have to get cos theta plus I sine theta. But if we multiply this out b times, then we just have cos a plus I sine a to the power of b, and we can use de Moivre's theorem, because b is a natural number, and we proved that case in the previous video. We can apply de Moivre's theorem to get cos ba plus I sine of b times a, and that must equal cos theta plus I sine theta. So now we can get one value of theta. We see that because the real parts are equal, then theta must equal b times a. Now that's one value for theta. As I said, there are multiple values of a, because we could imagine adding 360 degrees onto this, or 2 pi radians. Anyway, let's just take this particular value for a. So a is theta over b. So we can write this here as cos theta over b plus I sine theta over b, which can be got by multiplying 1 over b by theta. So we've proven that de Moivre's theorem is true when n equals 1 over b, where b is a natural number. Now at last we can prove de Moivre's theorem for n, an element of Q. So we can write any rational number as a over b, where b is a natural number. So we can always have b a positive integer. If we want to deal with something like minus 10 over 3, we can write it as minus 10 over plus 3. So we can have a natural number in the denominator. We can write any rational number with a natural number in the denominator. We can just take the minus sign on top. So now let's look at cos theta plus I sine theta to the power of a over b. Well, we can write it like this. We can write it as cos theta plus I sine theta to the power of 1 over b, all to the power of a. If we multiply these powers, we get back a over b. But we've already proven that cos theta plus I sine theta to the power of 1 over b, where b is a natural number, is cos theta over b plus I sine theta over b. And now we want to take this and raise it to the power of a. But a is an integer. It could be a positive or negative integer. And we proved that de Moivre's theorem also holds when the power is an integer. So we can multiply a in here. So multiplying a in, we get cos a theta over b plus I sine a theta over b. So we multiply a by the argument. But this means that de Moivre's theorem is true for n equals a over b. In other words, we can multiply a over b by theta. And we get this here. So we've proven de Moivre's theorem for all rational numbers. Now, it also happens that de Moivre's theorem is true for all real numbers. So it's true for irrational numbers as well. And complex numbers. I won't prove that.